Hello and welcome to this week's experiment, our last experiment of this class. For this experiment, we investigated the diffraction of light using a laser pointer, a CD surface, and a string to measure distances. The goal was to determine the wavelength of the laser based on the spacing of diffraction patterns. Our setup involved aligning a laser to shine through a diffraction grating and marking where the first order diffraction image appeared. We used string and a ruler to measure the two key distances, the distance between the central beam and the first order image, and the distance from the diffraction grating to the wall. As for safety, we followed all laser safety protocols. We avoided pointing the laser at anyone's eyes, worked in a controlled environment without reflective surfaces nearby, and secured the setup to prevent any misalignment. Measurements were taken with minimal movement to reduce error. Using the measured values of 72 millimeters and 100 millimeters, we calculated the wavelength using the grating formula. We assumed a diffraction grating with 1,000 lines per millimeter, so the space between lines was 0.001. After plugging in our values, the resulting wavelength was approximately 720 nanometers. This falls within the expected visible spectrum for a red laser, confirming that our setup produced reasonable results. If there was any error, it likely came from measuring distances by hand, especially the challenge of keeping the laser and string aligned or estimating angles. Misreading rulers or small shifts in setup could affect the accuracy of the wavelength. And for our second experiment, we have our graph right here showing the half-life decay, with our values of our scintillium from going from the parent atom to the daughter to the percentage of it remaining. So here are our values, the blue line representing our parent atom and its level of decay, to our daughter atom and the way that it increased. For the difference in spectra comes down to the nature of the light sources. A laser emits monochromatic light, meaning one wavelength, so when it reflects or diffracts off the CD surface, it produces a sharp clean dot or line in contrast. A flashlight emits a white light, which is a combination of many wavelengths. When this broad spectrum light hits the CD's grooved surface, this wavelength spread out into a rainbow-like pattern, as shown in here. This occurs due to diffraction, the separation of light based on wavelength. The CD acts like a diffraction grating, causing constructive and destructive interference that separates colors. Essentially, lasers show one color, flashlights show many, and the CD reveals this beautifully. And for a radioactive decay, it is predictable in terms of half-life. A half-life tells us how long it takes for half of a radioactive substance to decay. This allows scientists to make statistical predictions about large samples over time, which is how carbon dating and medical dosimetry work. However, radioactive decay is unpredictable at the level of individual atoms. We can't predict exactly when one atom will decay. It is random. We only know the probability that it will decay in a certain time frame. That unpredictability at the atomic level is what makes radiation safety important, since the energy released in any given moment could vary. So in summary, radioactive decay follows clear rules in large quantities, but each decay event is spontaneous and random on its own. And now to go into our most to least useful labs. I think for our most useful in supporting the understanding of the content, for me it was Module 9, this module, on the electromagnetic spectrum and half-life modeling. It was the most helpful for deepening my understanding of the key content. Measuring the wavelength of laser light using diffraction and modeling radioactive decay with Skittles made abstract concepts like wave behavior and half-lives tangible and interactive. Seeing how exponential decay worked in real time helped me solidify how unpredictable individual decay events are, yet predictable overall in terms of half-life behavior. Most useful in supporting my growth in the laboratory technique and or chemical safety was Module 4, which was the Precipitation Reactions Lab. It helped me develop the most in terms of lab technique. This was the first time I used gravity filtration and calculated percent yield, which gave me hands-on experience with measuring separation techniques and analytical reasoning. It reinforced the importance of careful measurements and clean technique to ensure accurate results and minimal product loss. For me, the least useful for supporting the lecture content was Module 6's Ice Cream Lab. Although very fun and delicious, it was the least useful in connecting directly to lecture content. While it was fun, as I said, and had chemistry applications like enthalpy and freezing point depression, the connection to deeper lecture material felt a bit superficial compared to the other experiments. It also wasn't very helpful that a lot of the experiment did not go as planned due to the lack amount of freezing point for the ice cream to actually solidify. It was more about the novelty than exploring the theory. And for least useful for supporting the development of my laboratory skills was Module 2 for fireworks. It was very basic, holding a loupe and a flame and observing colors. While it helped identify metal ions and reinforce the mission spectra concepts, it didn't really teach any complex procedures or safety protocols beyond basic flame. I hope you enjoy this post-lab, as it is our last, and I hope you have a very wonderful time. Thank you.